exploration of the atom, the essence of everything around us. In this segment, we journey into the microscopic world, where atoms serve as the fundamental building blocks of matter. But what exactly is an atom? Atoms are the smallest units of ordinary matter, forming the basis of all chemical substances and processes. They are like tiny architects, constructing the universe as we know it. Atoms are not just pivotal in chemistry, they are central to all scientific inquiry. Understanding atoms is crucial because they explain why matter behaves the way it does. From the air we breathe to the stars we gaze upon, atoms are at the heart of it all. This foundational knowledge sets the stage for delving deeper into atomic structures, subatomic particles, and beyond. Join us as we unravel the mysteries of atoms and their indispensable role in science. Stay tuned as we transition into the next segment, where we'll delve into the intricate structure of an atom and discover its hidden secrets. Imagine a world so intricate and precise, yet invisible to the naked eye. Welcome to the realm of atoms, the building blocks of all matter. At the heart of every atom lies its nucleus, a dense core packed with protons and neutrons. Surrounding this nucleus is a vast, dynamic space known as the electron cloud, where electrons whirl and dance in perpetual motion. Picture the nucleus as a bustling city center, where protons, each bearing a positive charge, reside alongside neutrons, which are neutral in charge. This central hub defines the atom's identity and stability. The protons determine an atom's element: hydrogen, helium, carbon, each distinguished by its unique number of protons. Now let's shift our gaze to the electron cloud, a region teeming with negatively charged electrons. These tiny particles move with remarkable speed and agility, creating a cloud-like formation around the nucleus. It's within this space that electrons interact with other atoms, forming bonds that construct molecules and ultimately the diverse materials we encounter daily. Understanding this structure is key to grasping the fundamental nature of matter. It's like unlocking the secret code that dictates how everything in the universe is formed and behaves. The interplay between the nucleus and electron cloud is not just a simple dance of particles, it's a complex symphony that defines chemistry, physics, and biology. As we delve deeper into the atomic world, remember that these minuscule components form the basis of everything we touch, see, and even breathe. From the air filling our lungs to the screen you're watching right now, every object is composed of atoms. This journey into atomic structure is just beginning. Next, we'll explore the subatomic particles that make up these atoms, each with its own distinct characteristics and roles in shaping our universe. In the vast tapestry of the universe, every single thing we see, touch, or even imagine is composed of tiny building blocks called atoms. But what exactly are these atoms made of? Let's dive into the fascinating world of subatomic particles and uncover the secrets that lie within. At the heart of every atom resides a tiny nucleus, a dense core that holds the majority of an atom's mass. Within this nucleus are protons and neutrons. Protons are positively charged particles, carrying a distinct electric charge that plays a crucial role in the identity of the atom. They determine the atomic number, which defines each element on the periodic table. Next to protons, we have neutrons. Unlike protons, neutrons carry no electric charge. They act as the stabilizers of the nucleus, ensuring that the protons, with their like charges, don't repel each other. The number of neutrons can vary in atoms of the same element, leading to the formation of isotopes. Surrounding this dense nucleus is a vast cloud of electrons. These negatively charged particles move rapidly in regions called electron clouds or shells. Electrons are much lighter than both protons and neutrons, yet they are essential for chemical bonding and reactions. The interactions between electrons of different atoms form the basis for chemistry as we know it. Together, these three types of subatomic particles, protons, neutrons, and electrons, come together to form the atoms that construct everything in our universe. Each particle plays a unique role, contributing to the properties and behaviors of the atom. The dance between these particles is what makes each element unique and allows for the complex interactions that form molecules and compounds. As we continue our exploration of atomic models in the next segment, we'll see how these particles fit into larger structures and how scientists have come to understand their behavior over time. Welcome back to our exploration of the atom, the fundamental cornerstone of matter. In this segment, we delve into the fascinating journey of atomic models. Over the centuries, scientists have crafted a variety of models to unravel the mysteries of atomic structure. These models illustrate how our understanding of atoms has evolved, highlighting the ingenuity and perseverance of scientific inquiry. Our story begins in the early 20th century, a time when the scientific community was on the brink of monumental discoveries. One of the pivotal figures in this era was Ernest Rutherford, whose model fundamentally reshaped our perception of the atom. Rutherford proposed that an atom is mostly empty space, with a dense, positively charged nucleus at its center, surrounded by orbiting electrons. This model was revolutionary, challenging the prevailing notions of atomic structure and opening new avenues for scientific exploration. Yet, science is ever evolving, and soon after Rutherford's breakthrough came Niels Bohr, who refined Rutherford's model with his own innovative insights. Bohr introduced the idea that electrons travel in specific orbits, or shells, around the nucleus, with each orbit corresponding to a discrete energy level. This notion provided a clearer picture of atomic behavior and laid the groundwork for quantum mechanics. Bohr's model was instrumental in explaining how atoms emit and absorb energy, leading to our understanding of atomic spectra. As we reflect on these groundbreaking models, it's important to recognize their enduring impact on modern science. They serve as a testament to human curiosity and the relentless pursuit of knowledge. Today, we continue to build on these foundational ideas with even more sophisticated models that incorporate advanced quantum theory and particle physics. The journey through atomic models is a vivid reminder of how scientific progress is built on a continuum of discovery and refinement. As we conclude this segment on atomic models, let us appreciate the remarkable journey from early theories to the intricate models we use today. Stay with us as we transition to our next topic, the periodic table and atomic numbers, an essential tool that organizes elements in a way that reveals their unique properties and relationships. Imagine a vast library of elements, each with its own unique story to tell. This is the periodic table, a masterful chart that unveils the secrets of the universe's building blocks. At its core lies a simple yet profound truth, the atomic number. This number isn't just a label, it's the key to understanding how elements are arranged and how they behave. Each element in the periodic table is defined by its atomic number, which tells us the number of protons in its nucleus. This singular piece of information guides us through the maze of chemical elements, like a compass, pointing us towards understanding their properties and interactions. The organization of the periodic table might seem like magic, but it's a precise system, meticulously crafted to reflect the nuances of atomic structure. Consider hydrogen, with an atomic number of 1 at the very top of this grand chart. As we progress through the table, each subsequent element adds a proton, gradually revealing more complex behaviors and characteristics. This orderly progression allows scientists and students alike to predict how elements might react with one another, unlocking new possibilities in chemistry and beyond. Furthermore, the periodic table isn't just an academic exercise. It's a powerful tool used daily by scientists to innovate and explore. From creating new materials to understanding the origins of matter, this chart is indispensable in the quest for knowledge. By understanding the role of atomic numbers, we can appreciate how elements fit together like pieces of a puzzle, each contributing to the grand design of our universe. This organization helps us not only categorize elements, but also grasp their potential in scientific applications. As we continue our journey through atomic concepts, remember that each element's place on the periodic table tells a story of balance between protons and electrons, a delicate dance that defines their identity. This understanding forms the backbone of chemistry and physics, connecting everything from the smallest atom to the largest star. Isotopes, a term that might sound complex at first, but once you unravel its meaning, it becomes a fascinating concept within the atomic world. Imagine you're looking at a group of atoms, each belonging to the same element. They share the same number of protons and electrons, which means they have identical chemical properties. However, lurking within their nuclei, there's a subtle difference. Some atoms carry more neutrons than others. These variations in neutron numbers give rise to what we call isotopes. Isotopes are essentially siblings within an atomic family, each with its unique mass due to the differing number of neutrons. This subtle variance doesn't alter their fundamental nature as members of the same element. Take carbon, for instance. In nature, it commonly exists as carbon-12 and carbon-14. Both are carbon atoms, yet carbon-14 with 2 extra neutrons is heavier and plays a pivotal role in radiocarbon dating, providing insights into the age of archaeological finds. Another example is hydrogen, the simplest and most abundant element in the universe. It has 3 isotopes: protium, deuterium, and tritium. Protium, with no neutrons, is the most prevalent form. Deuterium has 1 neutron, making it heavier and useful in nuclear reactions. Tritium, with 2 neutrons, is radioactive and finds applications in scientific research. This variability in isotopes extends beyond mere academic interest. It has practical implications too. Isotopes are vital in fields like medicine, where radioactive isotopes are used in diagnostic imaging and cancer treatments. They also serve as tracers in biochemical research, helping scientists track the movement of substances within living organisms. Understanding isotopes enriches our knowledge of elemental behavior and opens avenues for technological advancements. From determining the age of ancient relics to tracing metabolic pathways in biological systems, isotopes are indispensable tools in modern science. As we delve deeper into the atom's mysteries, isotopes remind us that even the smallest variations can lead to significant discoveries. In our next segment, we'll explore how these atomic building blocks manifest in everyday life, illustrating their role beyond theoretical concepts to tangible impacts on our world. Atoms are often perceived as abstract, but in reality, they are the fundamental components that make up everything around us. From the air we breathe to the ground beneath our feet, atoms are the building blocks of all matter. In this segment, we venture into the real-world application of atoms, highlighting their indispensable role in our daily lives. Imagine holding a simple object, like a wooden table or a glass of water. At their core, these everyday items are composed of countless atoms bonded together in intricate patterns. Each material's unique properties are determined by the types of atoms it contains and the way these atoms interact. Atoms not only form materials, but also drive chemical reactions that are vital to life and industry. Consider the process of cooking, where heat causes atoms in food to rearrange, transforming raw ingredients into a delicious meal. Or think about the combustion of gasoline in a car engine, where atomic interactions release energy that powers your journey. In the natural world, photosynthesis is another remarkable example. Plants convert sunlight into energy using atoms of carbon dioxide and water to create glucose and oxygen. Beyond natural processes, atoms are pivotal in technological advancements. In medicine, atomic structures are manipulated to create pharmaceuticals that target specific diseases at the molecular level. The importance of atoms extends even further into environmental science. Understanding atomic reactions allows us to tackle pollution and develop cleaner energy sources. Through innovations like solar panels and wind turbines, we harness atomic interactions to generate sustainable power. As we continue to explore the atomic world, we uncover new ways to innovate and improve our lives. The more we learn about atoms, the more we appreciate their role in shaping everything we know. As we draw our journey to a close, let's take a moment to recap the fascinating world of atoms that we've explored together. From the humble beginnings of understanding what an atom is to unraveling the complexities of its structure, each segment has built upon the last. We've delved into the heart of the atom, examining the nucleus and the intricate dance of electrons that surround it. We've met the subatomic particles, protons, neutrons, and electrons, each carrying their own unique charge and role in the atomic orchestra. Our exploration of atomic models took us through time, showcasing the evolution of scientific thought from Rutherford's revolutionary ideas to Bohr's groundbreaking model. The periodic table, with its orderly arrangement of elements by atomic number, revealed itself as a powerful tool for chemists and physicists alike. We saw how isotopes, those intriguing variants with different neutron numbers, add layers of complexity and richness to elements. In segment 6, we connected these atomic concepts to the tangible world around us, highlighting how atoms form the very essence of everyday materials. Now, as we conclude this exploration, remember that understanding atoms is not just a scientific endeavor, it is foundational to our grasp of the universe. Each concept we've touched upon today is a stepping stone to deeper knowledge. Science is an ever-expanding frontier, and the realm of atoms holds endless mysteries. So I encourage you to continue this journey. Dive deeper into the topics that piqued your curiosity. Whether you're a student just beginning your scientific voyage or an enthusiast with a thirst for knowledge, there's always more to uncover in the world of atoms and beyond. Thank you for joining us in this brief yet insightful exploration of atomic basics. Stay curious, keep questioning, and never stop learning. The universe is vast, and every atom within it tells a story waiting to be heard.